So if you have studied phase transformation, you know that when the phase transformation either from solid to liquid, which is called fusion, or from liquid to gas, which is called vaporization, is happening, the temperature remains constant, and all the energy which you provide or heat which you provide goes into breaking the bonds so that the phase transformation can take place. So this question concerns that, and we are going to look at how to correctly apply the latent heat of fusion and other concepts to solve this kinds of problem. Okay, so let's start. It says how much ice at minus 10 degrees Celsius must be dropped into an aluminum cup containing 300 gram of water at 20 degrees Celsius. Right, so there's an aluminum cup. It has some water, which is 300 grams of water inside, and it is at 20 degree Celsius. In order for temperature of the water to be reduced to 10 degrees Celsius, right? So final temperature is going to be 10 degrees Celsius, which means the delta T is going to be 10 degrees Celsius or 10 Kelvin simply. Okay. The cup itself has a mass of 150 grams. So the cup also has a mass, which is 150 grams, and it is made of aluminum, right? Which has specific heat capacity, 900 joules per kilogram per Kelvin. And we know the specific heat capacity of the water is 4200 joules per kilogram per Kelvin. Okay. And we are going to drop some ice into this, and we have to find the mass of how much ice we should be dropping. Okay. Now note the final temperature first. The final temperature is 10 degrees Celsius, right? So this ice is going to be dropped into this water and basically is going to melt and again form the water, right? But before the ice actually convert itself into the water, it has to go through the transformation of phase, right? So the ice, which is at minus 10 degrees Celsius, right? It will come to 0 degrees Celsius, okay? And then it will convert the phase transformation to water, and then the temperature will rise to 10 degrees Celsius, okay? So the process of how much energy will be required for this ice to be consumed has to be provided by somebody else, right? So that energy is going to come from the calorimeter, right? Or this aluminum cup, plus the water which is inside will lose that much energy, right? So our equation is going to be the energy required by ice to come to 0 degrees Celsius plus energy required for the phase transformation, right? Plus increase its temperature, right? So energy required to increase its temperature by 10 degrees Celsius, right? From 0 to 10 will be equal to, right? Provided by the energy lost by the aluminum cup by reducing its temperature from 20 degrees to 10 degrees Celsius. Also, the energy lost by the water, which is already there, to reduce its temperature from 20 degrees to 10 degrees Celsius, right? And by using this equality equation, we'll be able to solve the problem, right? So let's start by calculating how much is the heat or the loss of energy on the right hand side is, right? So we start from there, right? So energy lost by the aluminum cup, right? Our delta T here is 10 degrees, sorry, 10 Kelvin, right? Simply, the specific heat capacity for the aluminum is given to be 900. C is 900, right? I'm just not writing the units, and the mass is 150 grams, so M is 0.150, right? We multiply all of these three and we'll get our energy. So 0.150 into 900 into 10, and that will be equal to 1350 joules, right? So that's the first energy which our ice is going to receive. The second energy is going to come from the energy lost by the water, lost by water. Okay. So water's mass is given to be 300 grams. Okay. So that's going to be 0.30 into the specific heat capacity. We know it is 4200 multiplied by 10. Okay. And that will be equal to 12,600 joules. So in total, the total energy which these guys will provide, right, both of them is going to be sum of this, and that will be equal to 13,950 joules. Okay. Now, this energy will be used by the ice to do all the three things, right? First, to raise its temperature by 10 degrees Celsius from -10 to 0, and then to melt the phase transformation, and then again increase the temperature from 0 to 10 degrees. Okay. So for that, we are going to need the specific heat capacity of the ice, right? Which I know. Specific heat capacity of the ice is just half of the water it is. So this is 2100 joules per kg per Kelvin. And we are also going to need the latent heat capacity or latent heat of fusion for ice, right? Which is going to be used for finding how much energy is required for it to do the phase change. Okay. And that is, you can look at, that is 334 kilojoules, right, per kg. Okay, per kg, right? So let's start with the ice. So ice is going to start from -10 to 0 degrees, right? So my delta T is going to be 10, fine. And their specific heat capacity 2100, right? And the mass, let's say, is what we wanted to find. Let's the mass is equal to m. Okay. So how much heat required from -10 to 0 is going to be mass into 2100. Okay. Multiplied by delta T, which is 10. Fine. That's the first part. Then this, whatever mass it is there, it is going to convert it itself into water, and that will require mass into 334 kilojoules, which means this much energy required to convert into the water, right, from ice. And then the converted water will increase its temperature from 0 degrees Celsius to the 10 degrees Celsius, which is our final temperature, right? Our final temperature is 10 degrees Celsius, right? So that is going to be the mass of this water is again m, right? The mass is conserved, and then it is going to be 4200, right? The usual specific capacity of water, and then the temperature rise is equal to 10, right? Now we have this equation. You can solve this. So it's going to be m into 397,000, okay, joules, and that is going to be equal to the energy provided by the water and the aluminum thing, 13,950 joules. So, right. So the mass is going to be equal to 13,950 divided by 39700. Okay, this many kilograms, and this is going to be equal to a very small number now, right? So this is, you can compute that. One 13950 divided by 39700, and that is 0.0351 kilogram, or equal to 35.13 grams. Okay, and that will be our answer, that this much of ice is required to arrive at the things which we want to arrive at, right? So how much ice is required? Roughly 36 grams, right? So ice is going to first start from -10 degrees Celsius, come to 0 degree. We are going to use the specific heat capacity of ice for that, right? And then that ice is going to convert at 0 degrees Celsius to the water, and for that we have to use latent heat capacity of the ice, which we have written is 334 kilojoules. And then once it's converted to the water, the same mass is going to increase its temperature by 10 degrees, and that all that energy is going to come from the aluminum cup as well as the water which is inside the cup. And this is how we'll solve this problem.